Dear students, welcome to Brilliant Qatar. Today in this session, we are going to discuss some most important and probable multiple choice questions from the chapter Electric Charges and Fields and Electric Potential and Capacitance. So let's directly go to the questions. Question number 1. The unit of electric field is, you can see that it's a direct question, right? We have to recall what is the unit of electric field intensity. See, electric field intensity, the basic equation is, you know that E is equal to F by Q. It's a force experienced by a unit charge, right? F by Q. So if you're directly applying the unit here, you can see that the unit of force is Newton and the unit of charge is Coulomb. So you can see that the SI unit of electric field intensity, we are all familiar with it. It is Newton per Coulomb. But you can't see such a unit here. That means we have to use some other formula for the electric field intensity. Hope all of you remember, we have another relation, that is a relation between electric field intensity and electric potential. What is that? In a uniform electric field, you know that E is equal to V upon D, where V is the potential difference, D is the distance. So this is another familiar formula. So just substitute their unit, you know that potential difference, electric potential difference. What is the unit? It is volt divided by unit of distance. Distance is meter. So you can see that the SI unit, the unit of electric field intensity is volt per meter. That means the correct answer is, you can see that the correct answer is volt per meter. All right. Now let's go to the second question. Look at this. The electric field at a small distance r from an infinitely long plane sheet of charge is directly proportional to. I repeat, the electric field at a small distance r from an infinitely long plane sheet of charge is directly proportional to. See, you can see that it's a question from an important topic, that is applications of Gauss theorem. In applications of Gauss theorem, we have a clear idea, that is intensity of electric field due to a plane sheet of charge. Look at this. Let it be a plane sheet of charge and it's given some charge. So let us take this positive charge and the charge is uniformly distributed. And let the surface charge density be sigma. What is surface charge density? Surface charge density means it is charge per unit area. That means if you are taking unit area of this plate, within that unit area, how much charge will be there means that is sigma. That's the meaning of surface charge density. And you can consider any point P which is at a distance r from the sheet. Then we got a formula. We have derived a formula by using Gauss theorem. And what is that formula? E is equal to sigma by 2 epsilon naught. It's an important equation. Intensity of electric field due to a plane sheet of charge is sigma by 2 epsilon naught. So in this question, what they are asking is how this electric field is related to the distance. But you just look at the formula. In this formula, you can't see R. R is not there. What does it mean? That is, electric field is independent of the distance. It is independent of the distance R. Look at the option. Independent of means R should not be there. You can see option C. It is R raised to 0. That means R raised to 0 is 1. It is independent of R. Alright, so the answer for this question is, it's an important question. This answer is R raised to 0. Alright, now we can go to the next question. Look at this. A dipole is placed in a uniform electric field. Its potential energy will be minimum when the angle between its axis and field is. Another important question. Look, dipole is placed in a uniform electric field. So in a uniform electric field, a dipole. What is a dipole? All of us know that dipole is a pair of equal and opposite charges separated by a small distance. So such a dipole is kept in a uniform electric field. Then its potential energy will be minimum at which orientation? That means when the angle between that dipole moment and the electric field is. Look at the options. It's 0, pi, pi by 2, 2 pi. Alright. So let's go to the formula. Let's go to the formula for potential energy. Listen all of you. If there is a uniform electric field like this, so you can see the electric field is directed towards right. And in this uniform electric field, we are going to place a dipole consisting of two charges minus q and plus q. Theta is the angle between this dipole and electric field, then we have a formula for the potential energy. What is it? U is equal to minus P dot E, right? This is the equation for the potential energy. Now we can substitute, that P dot E is PE cos theta, right? PE cos theta. So this is the equation for potential energy of a dipole kept in a uniform electric field. Now what they are asking, this potential energy will be minimum. For the potential energy to be minimum, so let's check. Cos theta, what is the value of cos theta? Cos theta can be, that it ranges from -1 to +1. Okay, so the minimum value of cos theta is -1. And the maximum value of what? Cos theta is 1. So we will take theta as 0. So if theta is equal to 0, that's our option A. If theta is equal to 0, what we get? U is equal to minus PE cos 0, right? Cos 0. Cos 0 is equal to 1. So we're getting minus P. That's it. Potential energy is minus PE. Now if you're taking theta as 90, what we get? Potential energy will be 0. Theta is 180 means you'll get potential energy is equal to PE. That means if theta is 180, potential energy will be maximum, and theta is 0, what we are getting? Potential energy is minus P. Minus P means it's a minimum value. So the potential energy will be minimum when the angle between the axis and the field is 0 degree. Understood? So the answer for this question is 0 degree. Important point. Students, please note that in the same question, if they are asking potential energy is maximum at what angle? Maximum at what angle means if you are substituting theta as 180 degree, that means pi. 180 degree, what we get? Minus PE into cos 180 is -1, we'll get P. That is a maximum value. So please be careful while answering this type of question. So here, minimum when theta is equal to 0 degree. Alright. Let's go to the next. Look at this. Electric field intensity on the axis of an electric dipole when R upon A is very much greater than 1 varies as. It's another important question. It's based on, that intensity of electric field due to a dipole. See, we will take a dipole. Let it be the dipole. And it consisting of two charges. Here there is minus Q plus Q. Okay. Axis of the dipole. So axis of the dipole means this line, and you can mark any point P. This is the center of the dipole, right? So from the center, we'll take the distance as R. So we already calculated the intensity of electric field due to a dipole at a point on the axial line. What is the formula? E is equal to 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught into 2p by r cube. This is the equation, right? 1 by 4 pi epsilon naught, 2p by r cube. What is p there? P is the dipole moment. Now come back to the question. What they are asking, electric field intensity on the axis of a dipole varies as. So in the option, what we need to find is how does this electric field related to R? So here you can see that it's R cube. So clearly intensity of electric field is inversely proportional to R cube. So what is the answer here? You can see that it is varies as 1 by R cube. Alright, same question they can ask. Here it is on the axial. Same question they can ask on equatorial line also. Equatorial line, what is the difference? If you remember, the equation E is equal to 1 by 4 pi epsilon naught P by R cube. So the only difference is instead of 2p, there is P. In the case of equatorial line, there is P, but there is no change in the denominator. The denominator will be R cube. So no matter whether they're asking axial line or equatorial line, the answer will be the same. It will be 1 by R cube. Alright, so we are going to the next question. Look at this. A charge Q is enclosed within a cube. What is the flux through one of its phases? Another important question. A repeating question, and it is based on, that from the question itself you can understand. They're asking about the flux, and it is based on Gauss theorem. So let's check the question once again. A charge Q is enclosed within a cube. So inside a cube, we are going to place a charge Q. So let's take a cube. Look at this. Let it be the cube. And inside this cube, there is a charge Q. So we can mark a charge Q. It is inside. It can be at any point. There is no condition that the charge need to be kept at the center. It can be at any point. All right. Now what they are asking, what is the flux through one of its phases? They're not asking the total flux through this cube. Through one phase of this cube, how much flux will be there? All of you know that to apply Gauss theorem, we have to construct a Gaussian surface, right? What are the properties of a Gaussian surface? It has to be a closed surface. So Gauss theorem is applicable only for a closed surface. In this question, they're asking what is the flux through one of its phase. So look, I'm marking this phase. This is one of the phase of the cube, right? So if you're considering only that phase, we know that that is not a closed surface, it's an open surface, right? Gauss theorem is applicable only for what? Closed surface. So do one thing, we'll take the complete cube, okay? And apply Gauss theorem directly. According to Gauss theorem, total flux phi is equal to 1 by epsilon naught times the net charge enclosed by the surface. Net charge enclosed by the surface. So inside the Gaussian surface, total, how much charge is there? So from the question it is clear that only Q charge is there within that Gaussian surface. So the total flux through this Gaussian surface, that means the cubical surface, is equal to 1 by epsilon naught into Q. But they're not asking what is the total flux through the cube. They're asking what is the flux through one of its phases. You know that a cube has 6 phases, right? So this is flux through the entire cube, means it is a flux through the 6 phases of the cube. So this is a flux through 6 phases, but we need flux through only one phase. Now you can easily find it. Flux through one phase, if you are denoting it by phi dash, it will be equal to flux through 6 phases divided by 6. Alright, so what is total flux? It is Q by epsilon naught by 6. So we get Q by 6 epsilon naught. Look, it's option A. Q by 6 epsilon naught is the answer. So you have to be careful while answering this question. Sometimes the question will be what is the flux through the cube? Only flux through the cube. So if they are not mentioning flux through one phase, the answer will be Q by epsilon naught only. Okay, so I think it's clear. So we are going to the next question now. Look at this. An electric dipole is placed in a non-uniform electric field. What acts on it? Options are only torque, only force, both A and B, impulse. See, if you are considering a uniform electric field, look at this. This is a uniform electric field. In this uniform electric field, if you are keeping a dipole at any angle, we have already derived that, we got an idea. The net force acting on this dipole will be 0 because equal and opposite forces will be there. So net force will be 0, but there is torque. So you have to be careful. Dipole is placed in a non-uniform electric field. If the question is in a uniform electric field, our answer is only torque. In a uniform electric field, net force will be 0. The answer is only torque. But in this question, it is a non-uniform electric field. In a non-uniform electric field, definitely the net force will not be 0. It will not be 0, and at the same time, torque will also be there. So the answer for this question is both A and B. That means a dipole in a non-uniform electric field will be experiencing a net force as well as a torque. So our answer is both A and B. Students, be careful. Uniform electric field means only torque. Non-uniform electric field means it will be both force and torque. Let's move to the next question. Two plates are 1 centimeter apart and the potential difference between them is 10 volt. The electric field between the plates is. Two plates are 1 centimeter apart and the potential difference between them is 10 volt. It's a very simple question, you know that. See, the distance of separation between the plates is given as 1 centimeter and the potential difference between them, V, is equal to 10 volt. Okay, the electric field between the plates. What is the formula? What is the relation between electric field and potential? Electric potential, E is equal to V by D. V by D. So V is given as 10 volt divided by the distance as 1 centimeter. Have to be careful. 1 centimeter convert to meter. Centimeter is 10 to the power minus 2. So what we get? 10 into 10 square. That is equal to 1000. 1000, the SI unit of electric field, Newton per coulomb. So the answer is 1000 Newton per coulomb. You can see that. That's our option C. Option C is the right answer for it. Okay. Now, next question. Look at this. A charge Q is divided into two parts which are then kept some distance apart. The force between them will be maximum if the two parts are. It's a very simple question. Listen, all of you. There are two charges. Charge Q is divided into two parts, right? So let's go to the formula for the force. You know that Coulomb's law, right? F is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R square. So if there is a charge Q which are divided into, if you're taking one charge as small q, then the other definitely will be. So Q1 is equal to small q. Q2 will be what? Q minus q, right? So for example, if 10 coulomb is a given charge, that you can divide into 2 means if one is 1 coulomb, other will be 9 coulomb. If one is 2 coulomb, other will be 8 coulomb, like that. Then the force will be maximum under what condition? You know that the force is directly proportional to the product of the charges Q1 and Q2, right? It is directly proportional to the charges Q1 and Q2. Force is maximum means the product has to be maximum, right? Product is maximum. So if you are dividing a number into two parts, for the product to be maximum, that you can take any example, you can easily understand. The product will be maximum if that given number is divided into two equal parts, right? So if, for example, if 10 is a given charge, 10 coulomb is a given charge. If you are dividing into 5 coulomb and 5 coulomb, you can see that the product will be 5 into 5, that is 25. You won't get that number or greater than that for any other division. So what we get here is the force will be maximum if both the charges are equal. Both the charges are equal means first is q by 2 and the other is also q by 2. Understood? So the answer for this question is q by 2 each. Q by 2 each. Alright. So we are going to the next. The angle between the electric dipole moment and the electric field strength due to it on the equatorial line is another important and tricky question. Angle between the electric dipole moment and the electric field strength at a point on the equatorial line. So look at this. Let it be the dipole. Dipole consisting of two charges, minus q and plus q. So what is the direction of dipole moment? Dipole moment is a vector quantity, you know that. And what is its direction? Direction of dipole moment is from negative charge to positive charge. That means it is from minus q to plus q, right? Minus q to plus q. Minus q to plus q means here you can see that it is directed towards right. No doubt. Dipole moment is directed towards right. Now, what they are asking is angle between electric dipole moment. Okay, clearly you can see that the dipole moment is directed towards right, and the electric field strength due to it at a point on equatorial line. Where is equatorial line? Equatorial line is a perpendicular bisector, right? So look, let it be the equatorial line, perpendicular bisector. So I'm just taking a point on the equatorial line. Here is a point. At this point, what is the direction of resultant electric field? Hope you remember that derivation, and if you don't remember that derivation also, you can easily find due to this charge, due to the minus q charge, the field at this point will be, because electric field is a force experienced by a unit positive charge. So the resultant field at this, the field due to minus q charge will be in this way. Similarly, field due to plus q charge will be in this way, right? So two fields will be there. Now what we have to find is, we can find their vector sum. The vector sum of these two will be, if you are using the parallelogram law of vector addition, you can see that the resultant electric field is in this way. That's it. From this you can easily find the answer. Look at that. Dipole moment is directed towards right and the resultant field is directed towards left. Then what is the angle between these two? This is what they are asking here. Angle between the electric dipole moment and the electric field strength due to it on the equatorial line. That is, of course, I can understand it is 180 degree, right? One is towards right and other is towards left. So the answer for this question is 180 degree, right? So we can go to the next. Look at this. 2 point charges plus 9e and plus e are at 15 centimeter away from each other. Where should another charge q be placed between them so that the charge placed is in equilibrium? Okay, this is another repeating type question, condition for equilibrium. Alright, so let's start. Two charges are there. plus 9e and plus e, right, are placed at a distance of 16 centimeter away. Okay. They are kept at a distance of 16 centimeter away. Consider this. So, which is the first charge? You can see the first charge is plus 9e. Plus 9e. And the other charge is plus e. So, both are positive charges. They are, the distance of separation is given as 16 centimeter. 16 centimeter. Where should another charge q be placed between them so that the charge placed is in equilibrium? Charge placed is in equilibrium. So in between here, imagine, let it be the point where the charge placed is in equilibrium. So first of all, what is meant by equilibrium? When can we say that a body or a charge is in equilibrium? Equilibrium means, equilibrium in physics represent a net force acting on an object is zero. That's what the meaning of equilibrium. If the net force, the resultant force, that means the vector sum of all forces acting on a body is zero, means that body is in equilibrium. So here, on the charge small q, you know that there will be two forces, right? Because there are two charges, other two charges are there. Those two charges can exert force on this plus q, small q. So two forces will be there. If their vector sum means we have to consider the direction also, right? So first we will check what will be the force on q by 9e. If you are taking that as F1, this is a positive charge, this is also a positive charge. So clearly the direction of F1, it will be a repulsive force, so F1 will be towards right. So we will write the formula for F1. F1 is equal to 1 by 4 pi epsilon naught, right? Q1, Q2. What is Q1? 9e plus 9e. Q2 is q by the distance between them. It's not given. So we'll take it as x. So what will be the equation? It is 9e into q by x square. This is F1 and you can see that it is directed towards right. Now there is E charge on the right and Q again, the middle. So what will be the force between these two? E and Q. This E and this Q. Again, both of them are positive charges, so force will be repulsive, so F2 will be towards left. So clearly, you can see that F1 and F2 are oppositely directed. So oppositely directed means, now what we need to check, if their magnitudes are equal, net force will be zero. Direction are opposite, clearly in between these two charges, the directions of both the forces are opposite. Now if you can check whether their magnitudes are equal or if you are equating their magnitudes, you will get the answer. So we can write the equation for F2. What is F2? F2 is equal to 1 by 4 pi epsilon naught once again. Q1, Q2. What is Q1? It's E. Q2 is no change, it's Q only, divided by the distance. What will be the distance? Distance means distance between this E and this one. So total distance is given as 16 and we have already taken the left side, the distance between Q and 9E as x. So the remaining distance will be 16 minus x, right? 16 minus x the whole square, right? So we got the equation for two forces. Now what we can do? Just equate them. F1 and F2 will get the answer. At equilibrium, the condition for equilibrium is F1 is equal to what? F2. So what is F1? F1 is 1 by 4 pi epsilon naught 9e into q by x square is equal to 1 by 4 pi epsilon naught e into q by 16 minus x whole square. There are many things to be cancelled. 1 by 4 pi epsilon naught will be cancelled on both sides. Q will be cancelled. E will be cancelled. So the equation will be the resultant equation will be 9 by x square is equal to 1 by 16 minus x the whole square. And you can see that all are perfect squares, so you can directly take their square root. Square root of 9 is 3, square root of x square is x is equal to 1 by 16 minus x. What we have to find? We have to find the value of x, right? Cross multiply, get 3 into 16 minus x, that is 48 minus 3x is equal to x, that is 4x is equal to 48 x is equal to 48 by 4, that is equal to 12. So 12 centimeter, that's a value of x. X is equal to 12 centimeter. That means you can see, look at the diagram, x is the distance from which charge? Plus 9e. So plus 9e, 12 centimeter. So look at the option. 12 centimeter from plus 9e. Yeah. See, the option B is the right answer. 12 centimeter from plus 9e. Clear? Important question. So you have to practice it again and again. I'm going to the next question. Look at this. Two charged spherical shell does not produce an electric field at any. It's a concept-based question. The charged spherical shell does not produce an electric field at any. Hope you remember the electrostatic properties of a conductor. There are many properties of a conductor, right? Metallic conductor. What are the properties? First one is charge will remain only on the surface, right? Charge in the sense net charge, the excess charge, right? The excess charge will be remain only on the surface of a conductor. That's the first one. Number two is electric field inside a conductor is 0. Electric field inside. So that's the idea which we have to use here. The charged spherical shell does not produce any electric field at any interior point, inside. Outer point, beyond 2 meters, beyond 10 meters, definitely there will be fields. So the answer is interior point. Okay. Next. An electric dipole of moment P is lying along a uniform electric field E. The work done in rotating the dipole by 90 degree. Clear? Numerical. Electric dipole of moment P is lying along a uniform electric field. The work done in rotating the dipole by 90 degree. Okay, so there is a formula, direct formula for finding work done in rotating a dipole. What is that formula? Formula is work done W is equal to minus PE into cos theta 2 minus cos theta 1. You have to study this equation. Okay. Actually, based on this equation only, we got the equation for the potential energy of a dipole. So this is the formula. Now here, you may have some confusion. What are theta 1 and theta 2? Theta 1 is the initial angle. That means from the angle at which we are starting our rotation. That is theta 1, and theta 2 is the final angle. So let's check the question. An electric dipole of moment P is lying in a uniform electric field. So P and E values are given. Lying along a uniform electric field. So initially it is lying along the direction of the field. Along the direction of the field means what is the value of theta 1? Theta 1 is equal to 0 degree because it is lying along. And then the work done in rotating the dipole by 90 degree. Now it is rotating through 90. So theta 2 value will be 90. So starting from 0 and ending to 90. Now you can just substitute these values in this equation and get the answer. So W is equal to minus PE. Alright. Cos theta 2, cos 90. Minus cos theta 1, 0. That is minus PE into cos 90 is equal to 0. Cos 0 is equal to 1. Okay. So what we get? Minus P into 0 will be 0 and minus P into minus 1 will be P. PE. That's it. So the answer is PE. Option A. They can ask like what is the work done to rotate it from this position to 180 degree. So if they're asking 180 degree means you have to take theta 1 as 0 and theta 2 as 180. So like that, any question they will ask. So this is the formula. If they're asking work done to rotate a dipole means you can use this formula. All right. Okay. Next, a point charge A of charge plus 4 microcoulomb and another point charge B of charge minus 1 microcoulomb are placed in air at a distance of 1 meter apart. Then the distance of the point on the line joining the charges and from the charge B where the resultant electric field is 0 is. Okay, again a question based on the idea of equilibrium. We'll check. Two charges. One is plus 4 microcoulomb and the other one is minus 1 microcoulomb. They are at a distance of 1 meter apart. So the total distance will be 1 meter. Now what we have to find is the distance of a point on the line joining the charges and from the charge B. So this is charge A, this is charge B. From B, at what distance the resultant electric field is 0. So here you have to be very careful. First question is, will that point be in between these 2 points or not? So here one is a positive charge and other is a negative charge. So if you are considering a point in between, and imagine we are keeping a unit positive charge here, the field due to A will be, surely it will be towards right, because both are positive charges, and the field due to B will also be towards right, because one is positive and other is negative. That means they are not going to be cancelled. They both are in the same direction. Hope you understand. So the point where the field, resultant field is 0 will not be in between these two. So we can have that it won't be in between these two. Then where is the point? The other chances, look, what is the equation for the electric field? E is equal to 1 by 4 pi epsilon naught Q by R square, right? Q by R square. So we need to get a point where the two fields are oppositely directed. So let it be the point where the resultant electric field is 0. Let us assume like that and take this distance as x. So for what we can write is, we'll start from EA. So what will be EA? EA will be 1 by 4 pi epsilon naught. What is charge at A? 4 microcoulomb. So 4 I am taking, divided by the distance. Distance will be from A to P. The total distance we have to take. A to P means it will be 1 plus x the whole square. Okay? 1 plus x the whole square. And EB, field at P due to the charge minus 1 microcoulomb at B. So it will be 1 by 4 pi epsilon naught. Charge magnitude is 1 divided by the distance from B to P is x. So what we get? 1 by x square. Now the question is, we have to check whether they are oppositely directed or not. Look, at the point P, EA will be positive and positive. EA will be towards right. At P, the field due to B, EB, one is positive and other is negative. It will be towards left. Possible. They are oppositely directed. Now we can just equate it and then we can find the value of x. So EA is equal to EB. Then only the resultant field will be 0. Okay. EA is equal to EB. Substitute. What is EA? EA is 1 by 4 pi epsilon naught 4 divided by 1 plus x the whole square is equal to 1 by 4 pi epsilon naught into 1 by x square. These two will be cancelled. 4 by 1 plus x the whole square is equal to 1 by x square. Here you may have a doubt that we did not convert that microcoulomb into coulomb. In this case, no need to do like that because we are equating. Anyway, whichever unit comes, it will be cancelled on both sides, right? So now we can take the square root of these two. So 2 by 1 plus x is equal to 1 by x. So what we get? 2x is equal to 1 plus x. All right. So x is equal to 1 meter. X is equal to 1 meter, right? 1 meter. So look at the diagram. We have taken x as the distance from B, right? So from B at what distance? At the distance of 1 meter. So the answer is option C, 1 meter from the point B. All right. Next question is, the electric field required to exert a force on proton equal to its weight is. Electric field required to exert a force on proton equal to its weight. Okay. So listen here. There is a proton. Let it be the proton, and we'll take the charge of proton as Q and the mass of proton as M. So we need an electric field required to exert a force on proton equal to its weight. So force on proton should be equal to its weight. This is the idea. So if charge is Q, you know that the force due to electric field is QE. It will be equal to weight of a body of mass M is what? Mg, right? So Q is equal to Mg. So what they are asking is, what's the value of E? E is equal to what? Mg by Q. We will substitute. What is mass of proton? Mass of proton is 1.67 into 10 to the power minus 27 kilogram into G value we can approximately take it as 10 divided by Q, charge of proton, right? It is again 1.6 into 10 to the power minus 19 coulomb. Okay, so 1.67 by 1.6 almost equal to 1, then only the power will comes minus 27 and minus 26, so it will be 1.67 divided by 1.6 into 10 to the power minus 7 will be there, right? Yes, minus 7 will be there. So 1.67 by 1.6 will be almost equal to 1. 1 means, look at the option, it is, yeah, there is 1.02, right? Yes, so the answer is 1.02 into 10 to the power minus 7 volt per meter. Okay, next question. A charge Q is placed at the center of the line joining two equal charges Q. The system of three charges will be in equilibrium if Q is equal to. Alright, so listen here. Let it be the line. And a charge Q is placed at the center. So, Q is placed at the center of the line joining two equal charges Q. So, there is a charge Q here, there is a charge Q here. The system of three charges will be in equilibrium if Q is equal to. So, they are asking for the system to be in equilibrium, what will be the value of that small q? System in equilibrium. They are not asking that center charge is in equilibrium. Center charge, definitely you can understand it is in equilibrium because two equal charges are kept on its either side at same distance. So, definitely the net force on the middle charge Q will be 0. So, it is in equilibrium, no doubt. But they are asking this for the system to be in equilibrium. So, for this system to be in equilibrium, we have to consider some other charge. For example, let us take this charge. I am marking this point as A and this as B. We will take the charge Q at A. For the charge Q at A to be in equilibrium, the net force acting on that Q has to be 0. So, what we can take is, what will be the force on this Q at A by this capital Q. You can see that this is Q and this charge is also Q. They are identical charge. So, definitely the force exerted by one Q on the other will be repulsive, right? It will be repulsive force. They are identical charges. So, the force on this Q due to that will be in this direction. So, I am writing that as FB. FB is force on the charge Q at A by the charge Q at B. It is FB. So, I am writing its magnitude that you can easily write FB is equal to 1 by 4 pi epsilon naught Q1, Q2. Q1 is Q, Q2 is also Q divided by the distance. Distance between them, let us take it as R. So, what we get? R square. So, we have taken the total distance as R. So, R square. It is directed towards left. Now, for that charge to be in equilibrium, there should be one more force on that Q and it has to be towards right. And we are taking this point as C. So, we can write that force as FC. Remember, we need FC towards right. FC towards right means to get a force towards right, the force has to be attractive. For this charge has to be negative. So, keep that idea in your mind. Our center charge has to be a negative charge. So, if you are looking at the options, there are 4 options. Out of those options, only 2 options are negative. So, other 2 we can now itself we can skip option C and option D. Because the middle charge will be a negative charge. It has to be a negative. Now, we can write its magnitude. FC is equal to 1 by 4 pi epsilon naught Q1. What is Q1? Q1 is capital Q. Q2. What is Q2? Q2 is small q, right? Divided by the distance between these two will be R by 2 because it is kept at the midpoint, R by 2. R by 2. Whole square. Don't put minus q here because we are equating the magnitude only. Minus, the idea of minus we are using only to find the direction of force. It was already applied. Now you can equate because for equilibrium FB will be equal to FC. What is FB value? It is 1 by 4 pi epsilon naught Q into Q by R square is equal to 1 by 4 pi epsilon naught Q into small q by R by 2 whole square, which is R square by 4, right? Will cancel similar terms. 1q will be cancelled. R square will be cancelled. So, what we can see here is q is equal to 4q will come, right? So, q is equal to what? q by 4. So the magnitude of this charge is q by 4 and the sign we already got it is negative. So in the final answer there will be a minus q by 4. Minus q by 4. This is the answer for the question. Important repeating type. Okay, so the answer is minus q by 4. Remember, they are asking the system of the three charges will be in equilibrium. That's the reason why we have considered the equilibrium condition of the charge q at A. Okay, right. Next, look at this. Electric charge is uniformly distributed along a long straight wire of radius 1 millimeter. The charge per centimeter length of the wire is q coulomb. Another cylindrical surface of radius 50 centimeter and length 1 meter symmetrically encloses the wire as shown in the figure. The total electric flux passing through the cylindrical surfaces. Total flux, right? Total flux through the cylindrical surface. So here we can directly use the Gauss theorem. So what is Gauss theorem? The total flux phi is equal to 1 by epsilon naught q net, the net charge enclosed, right? Net charge enclosed. So here that cylindrical surface is what? Our Gaussian surface. Okay, then what we have to find is net charge. What will be the net charge? See, it is given that, all of you look at this question, the charge per centimeter length of the wire is q coulomb. So per 1 centimeter, in 1 centimeter, how many charge is there means q. In 1 centimeter length, to be careful, in 1 centimeter length, q coulomb of charge is there. But what is the length of this? It is given as 1 meter, right? So if in 1 centimeter q coulomb means in 1 meter means it is 100 centimeter, right? In 100 centimeter, how much charge will be there? Into 100, right? So q net charge enclosed by the surface will be 100 times q. Why 100 times means it is in 1 centimeter per centimeter length q coulomb. In 1 centimeter q coulomb. So in 1 meter is the length of that cylinder, the Gaussian surface. So 1 meter means 100 centimeter. So in 1 centimeter q means in 100 centimeter will be 100 q. Okay. So this is the net charge enclosed. Then you can easily apply that result here. So sorry, phi is equal to, right? Total flux phi is equal to 1 by epsilon naught into net charge. Net charge is q net is 100 q. So 100 q by epsilon naught. Look at this. That is option B. 100 q by epsilon naught. Clear? So these type of questions will come. You can always expect such a question like for application of Gauss theorem. So I'm going to the next. All right. Two spherical conductors of radii 4 meter and 5 meter are charged to the same potential. If sigma 1 and sigma 2 be the respective values of the surface density of charges on the two conductors, then the ratio sigma 1 by sigma 2 is. Another tricky question. Two spherical conductors of radii 4 meter and 5 meter. So there are two spheres, right? Two spherical conductors are there. Let it be the first one. And there is another one. Okay, now what is the difference between these two means? It is given the radius of the first one is 4 meter and the radius of the other is 5 meter. Okay, if sigma 1 and sigma 2 be their respective values of surface charge density, so sigma 1 is the surface charge density of the first one, sigma 2 is the surface charge density of the second one, right? And the important point to be noted here is charged to the same potential. So the potential on both the spheres are the same. Charge is not same. The potential is same. So if you are taking V1 as the potential of the first one and V2 as the potential of the second one, what is the given data is V1 is equal to V2. V1 is equal to V2. Okay. What is the formula for potential due to a charged sphere? If you are taking Q1 as the charge on the first sphere and Q2 on the charge on the other, the equation is V1 is 1 by 4 pi epsilon naught into Q1 by R1 is equal to 1 by 4 pi epsilon naught into Q2 by R2, because the potential due to a charged spherical shell is 1 by 4 pi epsilon naught Q by R. Alright, so here 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught gets cancelled. We get Q1 by R1 is equal to what? Q2 by R2. Okay. Now, charge is not given. We don't know the values of Q1 and Q2. But how can we find it? Look at that. Sigma 1 and sigma 2 are given. What are sigma 1 and sigma 2? They are the surface charge density, right? Surface charge density. What does it mean by surface charge density? Surface charge density is charge per unit area. Charge per unit area. So, per unit area of this spherical surface, there are sigma charges. Sigma 1 charges for the first one and sigma 2 charges for the second. Right? What is the total surface area? See, the equation for surface charge density is sigma is equal to Q by A. Charge per unit area, that is called the surface charge density. From this you can write Q is equal to what? Sigma times A. This is equal to sigma into what is surface area of a sphere? It is 4 pi r square. So Q is equal to sigma into 4 pi r square. Then what will be Q1? Q1 will be sigma into 4 pi r1 square. Q2 will be sigma into 4 pi r2 square. Now we can substitute that in this result. That means we got Q1 by r1, right? What is Q1? Sigma into 4 pi sigma. One second. Q1 will be sigma 1 into 4 pi r1 square. Q2 will be sigma 2 into 4 pi r2 square, right? So here we get sigma 1 into 4 pi r1 square divided by, already there is an r1. So from here only we are going to the step which is equal to Q2. Q2 is sigma 2 into 4 pi r2 square divided by r2. So 1 r1 will be cancelled, 1 r2 will be cancelled, 4 pi will be cancelled. Then what will be sigma 1 by sigma 2? Which is equal to R2 by R1. R2 by R1. R2 is the radius of the second one. You can see it is equal to 5 divided by radius of the first one. It is R4. So it is 5 by 4. 5 by 4. The answer for this question is 5 by 4. So the idea that we are using here is we are equating the potential formulas because it is given that they are charged to the same potential. So V1 is equal to V2. Okay. So the answer is 5 by 4. Next, according to Gauss theorem, the electric field of an infinitely long straight wire is proportional to. According to Gauss theorem, the electric field due to an infinitely long straight wire is proportional to. It is a direct question. It's a formula-based question. First application of Gauss theorem. In first application of Gauss theorem, we got an expression for intensity of electric field due to a line charge of linear charge density lambda, right? If linear charge density is lambda, what is the equation for electric field at any point P, which is at a distance r? So it is a uniformly charged line charge with uniform charge density lambda. Okay. The equation for E is equal to 1 by 2 pi epsilon naught into lambda by r. Okay. Where lambda is linear charge density. What is the meaning of linear charge density? Charge per unit length. In unit length of that conductor, how much charge will be there? That is called linear charge density. So here the question is, according to Gauss theorem, electric field of an infinitely long straight wire is proportional to. So how field is related to R? That's the only thing we have to find from here. Lambda is a constant, epsilon or 2 pi, everything are constant. So how E is related to R? Clearly you can see that E is inversely proportional to R. So the answer is inversely proportional to R. Right? Yeah. Next question. A metallic shell has a point charge Q kept inside its cavity. Which one of the following diagrams correctly represent the electric lines of force? So you know that this is based on the properties of field lines and electrostatic properties of a conductor. There are some very important points. One is electric field inside a conductor, inside a metallic shell is always 0. From that itself, you can easily find the answer for this question. There is a cavity inside a shell. So it's a solid shell, solid metallic shell, and inside there is a cavity. So cavity means just like free space. So over there the field will be there. So you just look at option A. In option A, you can see some field lines are passing inside that metal shell. It is impossible because the net electric field inside a shell is equal to 0. The same thing is happening for the diagram B also. There are some field lines. For D also you can see that. The field lines are passing through the, but look at option C. The field is there inside the cavity and then outside the shell, right? It's possible. Inside that solid metallic surface, there is no field lines. So our correct answer is option C. It's again a repeating question based on the properties of electric field lines. There is always a chance of asking question. Okay, hope it is clear. You can go to the next. Look at that. The minimum electrostatic force between two charged particles placed at a distance of 1 meter is. Minimum electrostatic force of repulsion between two charged particles placed at a distance of 1 meter. So here in this question, distance of separation is given. R is equal to 1 meter. If there are two charges, Q1 and Q2, kept at a distance R, we have the formula for the intensity of electric field E is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. So the value of 1 by 4 pi epsilon naught is 9 into 10 to the power 9, you know that, into Q1 Q2, Q1 into Q2 divided by R square. R is 1 meter here, so R square is 1 square. So look at the result, it is 9 into 10 to the power 9 into what? Q1 into Q2. This is the equation for E in this case. Sorry, force, minimum electrostatic force only they are asking. So it is not the field, it is a force, right? So F. Okay, but you may think that charge is not given, then how can we find the force here? Look at that, it is clearly mentioned minimum. For the force to be minimum, distance is already given, so we have nothing to do with the distance. For the force to be minimum, charge magnitude should also be minimum, right? What is the minimum possible value of charge? Is it 1 coulomb? No, right? You know that the basic charge is the minimum charge. What is the basic charge? Basic charge is electronic charge, right? 1.6 into 10 to the power minus 19. Okay, that's our value. So we have to substitute that value here. That is the charge of electron, the basic charge as a minimum charge. So it is 9 into 10 to the power 9 into what is Q1? Q1 is 1.6 into 10 to the power minus 19 into again 1.6 into 10 to the power minus 19. Okay, so we have to calculate it. So it is 9 into 1.6 into 1.6, right? 2.56, because 16 square is 256. 2.56 into 10 to the power minus 19 will be minus 38 plus 9 minus 29. 10 to the power minus 29 will come. So 9 into 2.56, right? 9 into 218 will be like 2.56. Around 23 will come. Okay, 23 into 10 to the power minus 29 will come. So that if you are checking it, yes, it is approximately 2.3 into 10 to the power minus 28 will come. Okay, so the answer is option A. Option A is the right answer for this. So I think the questions which we discussed in this session, everything is clear for you. This is the first part of the electrostatics session, and we will continue the rest of the questions. Some more questions are there to be discussed. The discussion will be continued in our next session. So keep watching.